Hello everyone, this is your SI leader Mark. Welcome to my MA 261 Fall 2019 Exam 2 walkthrough. So before we start with the first question, I would like to share with you my approach to solve exam problems. So first, I would like to identify the type of problem by looking at the keywords presented in the question prompt. The reason why I do that first is because on your exam, the question order will be shuffled, which means it's not going to be that your earliest content be the first question and then your latest content be the final question. It's all going to be shuffled. So it's really important that you identify what type of problems really quickly before you dig into the numbers. So once we identify the type of problem, I will show you the solving steps, which are each simple steps that you can take to arrive to the solution. And this solving steps can be applicable to any type of problems any questions of the same type. With that said, let's get started. So I would start with question, problem type, and keywords, and then solving steps. So let's read the question. Find the maximum value of the function f equals to 8x minus 6y subject to the constraint x minus 1 squared plus y squared equals to 1. So in terms of finding maximum value, minimum value, or aka the extremas of the function, we have three different types of problems. One is finding the local extrema, and also we have finding the maximum absolute extrema. And then in terms of finding the absolute extrema, we have the regular absolute extrema problems, and we also have Lagrange multiplier problems. So by reading through after reading the question, we notice that they want to find the constraint. So we all have a constraint. So that immediately tells us this is an absolute extrema problems. But our job is not done yet because there are two different types of absolute extrema problems. But by further inspecting the question, we can see that we have some sort of circular or elliptical constraint, right? So that's my first keywords here, right? Circular or elliptical constraint. And not just that, they want us to find the extrema, which in this case, the maximum value of the function subject to the constraint, which means they want us to find the extrema on the constraint, not inside the constraint. So we can use a Lagrange multiplier, or we can only use the Lagrange multiplier to find extrema problems, extremas on the constraint, and then we can only use them on circular elliptical constraint. So these two keywords tells me that this is a Lagrange multiplier problem. So now we know the type of problem, we can go ahead and solve for it, right? So let's start with the first step of solving a Lagrange multiplier problem. So first, I would do find grad f equals to fx, fy, and then fz. So that is the gradient of the function. And we also would like find the constraint of the gradient of g, and the g is the constraint function equals to 0. So gx, gy, and the gz. So we are given the function of f, which is f equals to 8x minus 6y, and our g function is just a constraint function and moving everything to the left hand side and leaving right hand side equals to 0. So in this case, we have x minus 1 squared plus y squared minus 1 equals to 0. We can safely ignore this part. So the gradient will be g of f. So in this case, it's a two variable function. So we are not going to have the z part. So I just try to be as general as inclusive as I can. So the gradient of f in this case equals to what? So that's just 8 and then minus 6, and then the gradient of g will be So let's do the power rule. So 2x minus 1 and then 2y. So now we have found the gradient of f and g, so we can proceed to the second step, which is set up gradient of f equals to gradient of g times the Lagrange multiplier. As well, so let's just set up this way. So so gradient of f, right, fx equals to gradient of g of x, fy equals to gradient, lambda, lambda of gy, and then fz equals to lambda of gz. So let's say, and then in this case, again, we don't have the z component because, again, two variable function. So if you look at this two equations, and then f and the g are functions of x and y, so that's two variables, right? And then, but do we know the value of lambda? No, we don't, right? So it's actually, we have three variables or three unknowns, but we only have two equations. This is a problem, this means we have more unknowns than we have equations. We cannot solve this system of equations. What are we going to do? Well, luckily, our constraint itself, the functions of g, is another equation that we can use to solve this system of equations. So let's include that. G equals to 0, right? So this gives us, let's just be general. If we have three variables function, we would have, x, y, g, including the constraint. So that's x, y, z, lambda. So that's four variables, and then we also have four equations. So we can also solve this system of equations. So that will give us 8 equals to lambda 2x minus 1, and then minus 6 equals to lambda 2y, and then g of z equals 0. I'm just going to quickly copy and paste here. And that's 3 questions, 3 unknowns. Right. So that means set of lambda f equals to, gradient of f equals to lambda gradient of g, and the constraint. Okay. So now we're just going to solve for x, y, z, and just to and I like to add this for the sake of completion. So we actually don't really need the value of lambda. So if we can, whenever we can, we will avoid solving for lambda if possible. All right, so I'll label this equation 1, equation 2, equation 3. And then from equation 2, right, you know what, I don't like this notation. Alpha, beta, charty. So from Bravo, right, we can see that, so from the, give me one minute. Yes, so in this case, we are going to divide A by B. So we will get A over minus 6 equals to lambda 2x minus 1, and then lambda 2y give us give us x minus 1 and then y. Let me add a new page here. And so that will give us negative 4 over 3y equals to x minus 1. So that will tell us that x equals to minus 4 over 3y plus 1. So what are we going to do with this x? What we're going to do is we are going to substitute this equation delta into Charlie. So that will give us minus 4 over 3 y plus 1, and then minus 1, right? They cancel out, squared, plus y squared equals to 1. I'm just moving the minus 1 over. So that tells us 16 over 9 y squared plus 9 over 9 y squared equals to 1. So that is 25 9 over 9 y squared equals to 1. Right? So I'm going to move this over. And then y equals to y squared equals to 9. Sorry, I'm dividing everything by yeah, okay, so that's not 3 squared and then 5 squared. So y equals to 3 over 5 and then minus 3 over 5. So that means that, so if y equals to these two numbers, then x equals to, then from equation number D right here, we know that x equals to negative 4 over 3 times 3 over 5, right? 3 over 5 is the value of y here, equals to, oh, sorry, I need a plus 1 as well. So that's 5 over 5 equals to, right, this cancel out. So negative 4 over 5 plus 5 over 5, that's 1 over 5. Negative 4 over 3 times negative 3 over 5, that, and then we plus 5 over 5. So 3 again cancels out, negative sign cancels out. 4 over 5 plus 5 over 5, that's 9 over 5. All right, so now we have obtained the possible values of y. So y and the x equals to 1 over 5 and 1 over 5 and then 3 over 5, negative 3, 9 over 5 and then negative 3 over 5. All right, the final, so the final step is plug the coordinates into your original function. Right, your original functions of f to find extrema on the constraint. So let's go back to our original function. F equals to a minus 6y. Right? So f of 1 over 5, 3 over 5 equals to, I'm going to, so that would be 8 times 8 over 1 over 5 minus 6 times 3 over 5 equals to 8 over 5 minus 18, so that's negative 2. I think. F 9 over 5 and then negative 3 over 5 equals to a times 9 over 5 minus 6 times negative 3 over 5 equals to, so the base, the denominator is 5 again. So that's 72 plus 18. So that's 90 over 5. That's 90 over 5. That's 18. So, I mean, to be honest, you don't even need to solve for this exact number again, because if the coefficient of a is, the coefficient, the greater your x, the greater your f, right? And then the smaller your y, the bigger your f. So let's see, right? The second coordinate right here, the x is greater than the x coordinate is greater than the one before it, and the y coordinate is smaller than the y before it. So obviously, this extrema will be larger. So we just need to solve for the second coordinate to get our 18, and that will be our maximum, sorry, the extrema. And that is the correct answer, alpha. All right, let's look at the second question. Evaluate this integral over region of this R, right? So again, let's start with identify the type of problem with keywords. So what I see is this is an obviously a double integral problem. This double integral and the dA gives it away. But we have two different types of double integral problems. So double integrals in rectangular regions, double integral in general regions, double integral in polar regions, and also we have some techniques for such as switching mode of integrations. So how do I know which type of problem it is? But we can start looking at the constraint here, right? So the constraint R is x bounded by 1 and 2, and the y is bounded by 0 and 4. So this tells me that the bounds are constant. So this is telling me that this is in double integrals in rectangular regions. So the keywords are constant bounds for both variables, and then the problem type is obviously the double integrals in rectangular regions. So the solving steps, I'm just going to give it away. But before I show you these two steps, I'm going to tell you that the 0 step is for any type of double integrals or triple integral problems. As easy as it is, as easy or as hard it is, I would highly recommend you to draw the region out. So in this case, I'm going to do the same, right? Draw the region. So, okay. So our bound, so let's start with x-axis, and this is my y-axis. So 1 is right here, and then 2 is right here, and then 0 is right here, and then 4 is right here. So I think everybody would agree that this will be my region of integration, right? So stretching from 1 to 2, and then region from 0 to 4. I always draw regions, as easy or no matter how easy or how hard it is. So then the first step is pretty easy, right? So I'm not gonna spend too much time on it. So first step is treat other variables as constant and work your integrals inside out. So let's set up the problem, right? So double integrals x squared y 2 plus x cubed. What do you want to do? I think I'm just gonna go with dy dx because why? because I think it's pretty easy to start with integrating with y, because y is just y standing alone right here, and then I can like evaluate the y integral first and then treat it as a constant when integrating with dx. So let's do that. So that means our integral will be the integral of dy. So the y bound integral is always, bottom to the top, right? So what is my bottom bound of the region? So that's 0. And what's my top bound of the region? And that's obvious 4. And when I'm integrating with dx, I'm integrating from left to right, left to right. So what is my leftmost bound? And that is just 1. And what's my rightmost bound? And that is just 2. All right, so let's move this integral over. So, so I can rewrite this integral as, I'm going to copy and paste. That makes it faster. I can rewrite this integral as like this, right? So I'm just going to treat everything here as a constant for now and work my y integral. So that will give me 1 to 2 y squared over 2, right? I'm just moving everything down. Y squared over 2, 0 to 4. And that will give me, I'm going to move this a little bit to the other side. Hopefully you all understand. I'm going to write 2 integrals in one line. That will give me 1, 2, and then this integral. And the integral over here, right? So y squared over 2, you evaluate at the 4, that's 16 over 2, that's just 8. And then substitute with 0, and that just gives me 0. So that is just a constant 8 over here, right? Remember, this is our y dy, 0 to 4, and then dx. So, okay, this is a little bit tricky, right? So this requires something that we learned from Calc 1 and Calc 2, and that is u substitution. So let's set up u equals to the denominator, 2 plus x cubed. So du equals to 3x squared dx. So what is dx equals to, right? So dx just equals to du over 3x squared. So we're just moving the 3x squared to the left-hand side. So we are going to substitute this dx right here, and then we're going to substitute dx over here, and we're going to substitute the u over here. I think everybody following. I think everybody's following, right? So 1 over 2, I'm moving the constant out. So that's x again, right? So I'm moving x squared over 2 plus x cubed. That is just u, du over 3x squared. And then this 2 cancels out, so that gives me 1, 2, 8. Actually 8 over 3, right? I'm moving the 3 over here out as well. So that's just 1 over u du. Oh, actually the bounds is not supposed to be here because our variable has changed. And this is just simply logarithmic integral, right? So this will give us, integrating this integral will give us the natural log function. So 8 over 3 natural log of u, which is 2 plus x cubed, and then from 1 to 2, right? So we're just going to substitute 1 and 2 in. So that's just equals to 8 over 3 natural log. So 2 plus 8, right? That's 2 to the cubic, so that's 10. And then minus natural log of 2 plus 1, that's just natural log of 3. So this is our final integral. So if you look up, right, so then this is the correct answer. Number Charlie is our correct answer. But if you simplify this thing even further, right, so we can use the property of natural log, right? So we can rewrite this as 8 over 3 natural log of 5 minus natural log of 1.5, and this will be the the expression on the right hand side is the same thing as the expression on the left hand side, and this will yield the this will give us that the answer echo is also the correct answer. They are essentially the same expression, just one is more simplified than the other. So this is how you suppose. This is question number 2. All right, question number 3. Evaluate this integral by switching order of integration. So first of all, by looking at this integral, right, it's dx dy. So that tells us something about it's an double integral, right? Double integral dx dy, and it's in a rectangular coordinate, right? At least that's what it seems like. So dx dy to give something away, right? At least it's something in the rectangular region. And look at the bounds, right? Look at the bounds. Are those bounds constant? No, they're not, right? They are functions of something, at least in the inner bound. So that tells us it's a long rectangular integral region. And the final thing, which is the most obvious, which gives the question away, is reversing the order, right? Switching the order of integration. So this tells us that it is a double integrals in general regions, right? The region is non-rectangular, and the question is also asking us to reverse the order of integration. So the first step is, again, draw the region of integration. But what can we use to help us to draw the region of integration, right? There's not, they didn't give us explicitly what the bound is, but can we find it? Absolutely. And the way we can find it is by draw the region based on the integration bound. Right, so let's draw this big rectangular Cartesian coordinate x and y. So give me a second. So what is this 2 pi mean? So this is the upper bound of the upper bound of the dx integrals, right? So that is x2, and this is x1, and this is obviously y2, and this is obviously y1. So x1 equals to y squared, and then x2 equals to 2 pi, and then y2 or y1 equals to 0, and then y2 equals to root of 2 pi. So let's start with the y bounds, shall we? Because they're constant. So that helps that makes our life a little bit easier. So that y1 equals 0 right here, and then y2 equals to 2 pi, right? So y2 equals to 2 pi square root. 2 pi square root right here. But let's draw this x1 equals to y squared, right? That's kind of hard to draw, right? But we can make y explicit by square rooting both sides, right? So y equals to square root of x. So this is square root of x. Okay, because it's and also the x bound of 2, and that is and this is, let me make this dash 2. So that is 2 pi, right? So x equals to 2 pi. So where is the region of integration, right? So so x1 equals to y2. So this curve is the lower bound of the x, and x equals to 2 pi, and this is the upper bound of the x region. So when we integrate x, we always integrate from left to the right, right? So left bound to the right bound. So we can conclude that this is the region of integration. Okay. Oh, one more thing. Usually, when they tell us when the question tells us to reverse the order of integration, the integral is usually impossible to solve analytically. It's usually impossible to solve analytically if you don't reverse the bound of reverse the region of inverse the order of integration. So we must reverse the order of integration to solve the problem. So now we know the region of integration. So the second thing is, right, we need to figure out whether the original integral, right, OG integral, assumes horizontally simple or vertically simple. So horizontally simple HS or vertically simple VS. All right, so let's copy the integral over. Okay, so the easiest way that we can tell whether this integral assumes horizontally simple or vertically simple is by looking at the first variable of integration. So if you integrate with dx first, so x is going, horizontally, right? So that integral assumes horizontally simple. And if the integral start with dy first, so dy is up and down, right? So that means the integral assumes vertically simple first. So obviously this case is dx first. So it's assume horizontally simple. So then what we're going to do is we need to change the order of integration from horizontally simple to vertically simple. So that means from dx dy to dy dx, right? So, all right, so let's set this aside. All right, so the third step is change the order of, change the bound, of inner integral. So if, let me add one more page here. Right, if it's horizontally simple, the bounds of integral should be functions of y. So bounds of inner integral should be functions of y never mind. This means it's vertically simple. I take that back. Right, so it's horizontally simple to vertically simple. I make that mistake. Sorry about that. So if it's vertically simple, so the bounds of inner integral should be functions of x, right? So that means we need to have f f1 x and f2x, or just y1x and y2x, right? So it's a function of y. That means lower bound y1x is the bottom of the region and then upper bound y2 is the top of the region. Let me highlight these two things. Right, so lower bound, upper bound. Okay, so let's go back to our region that we just drew here. So where is the lower bound? So the lower bound is right here, right? I think everybody can agree that the very bottom of the region of integration is right here. And that is just, and then in terms of functions of y, and that is just functions of y equals to 0. Right, so that y equals to 0. And then the upper bound is this curvy thing right here, right? So when we integrate it from the bottom to the top, right, the line always reach this, the vertical line is always reaching this curve. And that curve is y2 equals to square root of x. All right. So let me write this down. So y1x equals to 0, and then y2x equals to square root of x. And then the fourth step is to obviously find the bounds of the outer integral as constants. And this is pretty easy. So we're just looking at what is the leftmost and what is the rightmost of the x coordinate. So the leftmost coordinate is 0, and the rightmost coordinate is 2 pi. So x1 equals to 0, and then x2 equals to 2 pi. So let me label it right here as well. Let me just use a different color. X1 equals to 0, and then x2 equals to 2 pi. All right, so let me label this pink, and then label this blue. All right, then the final step, right, that you've been waiting for, right? So that's just assemble the integral and integrate. So the final integral will just be y1, right, equals 0, y2 equals to square root of x, and then x1 equals 0, and then x2 equals to 2 pi. And then the integrand is y cosine x squared dy dx. So let's go back. Let's see if I'm correct. Okay, so y squared cosine x squared dx dy dx. All right. So let's evaluate this integral really quickly. Dy dx, again, we treat x as a constant, so that will give us 0 to 2 pi cosine x squared y squared over 2 0 to square root of x. So that will give us 0 to 2 pi cosine x squared x over 2, right? So square root y squared, substitute by square root, that just gives us x, and then divide by 2, and then the lower bound just yields to 0. Okay, so this is where we need to do the u substitution, right? So I'm gonna say let u equals to x squared, du equals to 2x dx, dx equals to du over 2x. And let's substitute this in. That will give us cosine u, and then x over 2 du 2x. And that will give us cosine u over 4 du. And that's just obviously cosine, right? Sine of u, which is x squared over 4, and 0 to 2 pi. And that's just, let me expand this integral really quickly, because this is where most people make mistakes on this question. And then unfortunately, this happened to me when I was taking the exam in fall 2019. I took MA 261 in fall 2019, and I was in a hurry, and I didn't I wasn't very careful with the algebra. So let me just expand this and not make the mistakes. So sine x squared, that's 4 pi squared over 4. This should not be simplified further. This is not the same thing as sine of 4 pi, and that equals to 0, and this is not. And then minus sine 0 over 4, and this is 0, so this can be canceled out. So that's just the final answer, just sine 4 pi squared over 4. And then that's the correct answer. Delta. All right, question number 4. Let D be the solid region bounded by the planes x equals to 0, z equals to 0, y equals to x, and then x plus y plus z equals to 2. Which of the following integrals is equal to the triple integrals for all continuous functions defined on region D? So by looking at this question, I noticed that all of the answer choices are dd, dy, dx. So that tells me this question is, the answer should be expressed in the rectangular coordinates. So the first thing that gives it away is the differentials the dv's are in rectangular, and this is pretty much all you need to know. Plus the fact that all of these bounds are expressed in the rectangular region as well, rectangular Cartesian coordinates as well. So this is obviously an rectangular triple integrals in rectangular region. So let's start with solving steps. So first step is draw the region as usual, right? And for triple integrals, especially in rectangular coordinates, we have two types of drawings that we can use to help us to find the bounds of the integral. So the first one is traces. All right, so if lower z bound equals to 0. And you might wonder, right? We have xy trace, xz trace, yz trace. Which one is going to be the most helpful? So the way to tell that is the most helpful trace has intermediate variable as the vertical axis. And outermost variable I'll say integration variable. How about that? Integration variable. As the horizontal axis. All right, so okay, now what does this mean, right? So let's put this sentence to practice in our question. So let's go ahead and then draw our axis, right? So let's draw our axis. Extend that a little bit, and so what is the intermediate integration variable in our question, right? So all of you notice that all of the integration are dz, dy, dx. So the intermediate variable in this case is dy, so y will be our vertical axis. So let's put the y right here. And the outermost integration variable, dx, will be our horizontal axis. So that will be our x. So this is the most helpful trace that we can draw to help us find the bounds of integral. Of course, if you like, you can draw the rest of the traces to help you complete the picture, but I think this is the most efficient way to find the bounds. So, okay, let's look at our bounds, right? Our bounded planes. So x equals to 0, z equals to 0, y equals to x, and x plus y plus z equals to 2. All right, let's move this over. So x equals to 0, right? So x equals to 0 is right here. And then z equals 0, of course, we cannot show that in our xy trace, but it will be helpful later. Y equals to x, let's label this as blue, or label this as, label this as, blue. So that will be something look something like this. Y equals to x. And then x squared plus x plus y plus z equals to 2. Well, this is a 3D plane, right? And obviously this is a plane equation. But what we can do with it is finding the xy trace of the plane. So we take z equals to 0, will give us x plus y equals to 2, and then y equals to 2 minus x. So 2 minus x is looks something like this, right? So y equals to 2 minus x. So the y-intercept of this line will be 2, and the x-intercept of this line will be 2. This should be pretty easy. And then the intercept point between the blue line and the purple line, y equals to x and y equals to 2 minus x, this should just be x equals to 1, right? So the second drawing we can draw is isometric view. What does that mean? If possible and helpful. Okay, so what I mean by the isometric view is looks something like this. I'm pretty sure your professor has drew something that looks like this. So x, y, and z. So intercepts, right? So we can use the concept of intercepts that you learned earlier in our course. To help us draw the isometric view. All right. So, but today I think, but let's just go back to 1.1, trace region 1.1. So, so if you notice that, if you look at the drawing that we have here, right? So the region is bounded by x equals to 0, y equals to x, and then 2 minus x, y equals to 2 minus x. So the common intercepting region of these three lines is just this little, it's just triangle right here. Let me make this line a little bit thinner. Right, so this will be our region of integration, at least on the 2D case. So, right, by looking at this integration, I would say it's pretty difficult for me to draw this thing in 3D by hand. So I'm gonna skip that for today, but of course, we're gonna skip that for today. But I'm going to show you that finding the 3D bounds is going to be very, very easy for you. So, okay, let's go ahead and find the bounds. All right, step 2, find bounds. So 2.1 traces contain, right? The whole point of drawing the traces is to help us to find the bounds, right? So they contain one-dimensional and two-dimensional information, and helpful to find the constant bounds. Right, so that is the outermost bound. And the intermediate bound. Right, so the bounds in the middle. So, right, let's go back to this trace diagram that we drew just now. So the question answer choices want us to find the dy dx, right? So the x dx will have constant bounds. So let's start with that first. So if you can see that dx is this way, right? So if we draw our lines in this region, so the lowest we can go is x equals to 0, and then the rightmost we can go is x equals to 1. So that tells us that x1 equals to 0, the lower bound, and x2 equals to 1, the higher bound, the upper bound. And for the y bound, right? So let's draw the vertical lines, right? And then reach to the top of the region, from the bottom of the region to the top of the region. Y equals to x, right? If we draw these straight lines, we can see that our lines always touches the blue line at the bottom and the purple line on the top. So that means the lower bound is y over x, so y equals to x, right? So y1 equals to x, and then y2 equals to 2 minus x. So, right, so you can see that, these two x bounds are one-dimensional because they are constant, and then the y bounds are two-dimensional because they contain two variables now. So let's go to our isometric view. Right, so isometric view, iso view contains, as you guessed it, 3D information. And then this is helpful for us to find the innermost bounds. Right, so the innermost bounds. So how are we going to do this? Because we obviously skip the isometric view, but we can still, by looking at the information that are presented to us, right? So which two planes, right? Which two bounding planes contains the variable z, right? So obviously this is one of them, and this is the other one. So let's move them down, right? Z equals to 0, and then x plus y plus z equals to 2. I think I'm correct, right? X plus y plus z equals to 2. So we can turn this into z equals to 2 minus x minus y, right? I think everybody can agree with that. So if we plug in if we plug in some small x and y values, you would realize that z is a positive number, right? So that tells us in some conditions, in the conditions, especially defined in our by constraint, right? So let's just pick a small number right here, right? So x less than 1, y minus 1. So the z, it will be definitely be greater than 0. So this tells us that, so by looking at these two equations, we can conclude that z1 equals to 0, and then z2 equals to 2 minus x minus y. All right. So finally, we can assemble the integral. And integrate. Right, so 3 big triple integral, right, and then your f x y z dz dy dx. So our x bounds will be 0 and 1, right? So these are your color in brown, and then your y1 will be x, y2 will be 2 minus x, and then your final bound will be, let's make this purple. Right, so z1 will be 0, and then z2 will be 2 minus x minus y. And if we go up to our answer choices, we'll find Bravo, answer choice B. Answer choice B will be the correct answer. So that is question number 4. All right, question number 5. Evaluate the integral using cylindrical coordinates. So obviously this question wants us to use cylindrical coordinates to solve this problem. So that's my first keyword. But what if it doesn't say? What if it doesn't say this evaluate using triple integral, cylindrical integral? What if this doesn't exist? How can we know that using cylindrical coordinate will be helpful for us, right? So let's take a look at the bounds of an integral, shall we? So immediately I see something x squared plus y squared, and then what is x squared plus y squared equals to r squared, right? And e squared, and then when you put a square root on it, so that's just a square root of x squared plus y squared equals to r. So I'm seeing and also it's same thing. It's same thing over here, right? Now instead of just r, that's just 2r. Square root of r, right? Square root times r. Square root of 2 times r. So I'm seeing lots of x squared plus y squared equals to c squared, x squared plus y squared equals to r squared, and then square root of that equals to r. I'm seeing a lot of this similar expressions. So this is hinting me to switch to cylindrical. And what you notice is that if you look at once we draw the region out, we will notice that this will become a partial or circular or partially circular region of integration. So that tells us, it's better to use cylindrical coordinates to solve this type of problem, right? Partial circular region of integration, that tells us that, hey, this is a cylindrical coordinate problem in triple integral. All right, so as usual, for solving any type of double integrals and triple integral problem, we are going to start with draw the region. All right, so again, I'm just going to copy and paste what we did for question number 4 down below. All right, so traces All right, let me go ahead and read it for you first. Right, so copy and paste. So trace this, right? If the lower bound, the z, equals to 0. In this case, it is anyway, let's ignore this statement for now. But let's read the pink part. The most helpful trace has the intermediate integration variable as the vertical axis and the outermost integration variable as the horizontal axis, right? The intermediate integration variable is y here, so y will be our vertical axis of our trace, and the x is the outermost variable, so that will be the x coordinate of the trace, horizontal axis of the trace. So we are going to draw a YZ trace right here. Sorry, YX trace. We're going to construct we're going to draw the region by looking at the bounds of an integral, right? So our dx is bounded by 0 and 2. So let's start with that. So x equals to 0 and x equals to 2. And our y bounds is, so this is, right, this is x2, this is x1, this is y2, this is y1, and this is z2, this is z1. So let's look at y2, right? So y2 equals to square root of 4 minus x squared. So if we square both sides, we will get y squared equals to 4 minus x squared, and then x squared plus y squared equals to 4, right? So this is obviously a circle. So you should be familiar with the self, right? By looking at something that in this formula, in this term, in this style, to hey, this might be a circle. This might be a circle, equation of a circle. So let's move it down. Right, so y2 is something like this, right? It's a circle. I'm just gonna draw the whole circle. Oops, let me disable the fill. Right, so this is a circle radius of 2. So this is 2 right here, and and this is 2 right here as well. So, is our integration, region of integration, the whole circle? No, I don't think so, right? Why? Because first of all, if you look at the y1, right, y1 is 0. So the lowest y coordinate we can go is y equals to 0. So that effectively eliminates all of the region at the bottom, right? So they don't belong to our region of integration. And look at our x bound, right? Where does our x coordinate go to, right? The x coordinate can go only to x equals 0, right? The x coordinate cannot be negative. So we effectively eliminate this region from our region of integration, right? So now our integration region on the 2D projection is just going to be this this circle right here, this quarter circle right here. So let me just fill that out for you. Right, and that's pretty much all we need to do for the traces. And then let's shift our attention to of these d coordinates. So, well, if you notice that the region of actually today we're also going to skip the isometric view. The reason being that if you notice that the region of the order of integration for cylindrical coordinate is just going to be d, z, d, r, d theta, right? Oops. So d theta. So the r effectively doesn't change. All we need to do is to express the z in terms of cylindrical coordinate variables. So there's no need to alter anything or to find it. It's already here for us. We just need to change its expression. So, but just for the sake of completion, right, we're going to copy and paste this isometric view that we had for question number 4 to down below. Luckily, but still, I would highly recommend you to draw them out if you can. But we're gonna skip for the sake of convenience. So let me delete this. So once we draw the region, we're going to find the area of integration. Area of integration, we haven't found it. So we're gonna skip that. So the third step is to find. The second step is to find the bounds of integration using the trace, right? So the trace can help us to find the bounds of theta and r. Let me add one more page here. So let's go back to the traces, shall we? So the way I like to find the bounds of r's and thetas is I like to shoot out lasers. I like to use the idea of using lasers. So let's say I'm shooting a laser out right here, right? So what's the lowest? What is my starting point? My starting point is r equals to 0, right? Because I'm at the center, and I can shoot a laser out. How far can a laser shoot to? The obvious answer is I can shoot my laser out to a radius of 2, right? Because it's bounded by this blue circle. So that means r is bounded by 0 and 2. So I'm just gonna say r1 equals to 0 and then r2 equals to 2, right? But let's go back to the laser again, right? Instead of looking at its length, let's look at these angles, right? So what is the angle I can shoot to right here? Obviously, theta equals to 0, right? And I can rotate my laser, increase my theta, and then boom, I get stuck here. And what is my theta at this angle? And this should be obviously pi over 2, right? So theta 1 equals to 0, and then theta 2 equals to pi over 2. Again, let's make them, let's color code them as we go. And again, we don't need to convert the z bounds. So we're just going to convert. So the third step is convert the bounds of the z2 x y z z1 x y z into polar, right? So that will give us z2 equals to something of z2 of r and theta, and then z1 equals to z1 r and theta. So what does that mean? Right, let's go back to our example again. Right, so what is my z2? z2 equals to square root of 2x squared plus y squared, right? And that's equals to square root of 2 of x squared plus y squared. And z1 is just simply x squared plus y squared. And then what is the conversion from, and I mean, obviously we can just using the rule right here, right? The rule of x squared plus y squared equals r squared, convert it into cylindrical. So this equals to square root of r, and then this one is just r. And then let's move this to the bottom. And that completes our step 3. So step 4, convert the integrand into cylindrical. You know what? Let's change this to cylindrical too. All right, so do we have one? Obviously, we don't have one, so just 1 equals to 1 in this case. And then finally, actually, the final step before we assemble the integral is step 5, convert the differential into polar, cylindrical. Okay, so dv equals to dz dy dx in rectangular. That becomes r, right? Don't forget about the r. I'm highlighting it for you so that you hopefully don't forget in your exam dz dr d theta. All right, so that completes everything that we need to do before we assemble the integral. So that's the final step. Assemble the integral and integrate. Okay, so, right, 3 big integrals. And then 1 d r dr dz, dz dr d theta. Okay, so the theta bounds will be the outermost, so that's 0. So 0 to pi over 2. And then r is just 0, and then r2 is 2. Let me color code this as well. 0 to 2. And then outermost z bound is just r and root 2r. And then let's go ahead and integrate this really quickly. Right, the rest is history. That's just gonna give me r, right? So let me copy the integrals over. R root 2r minus r dr d theta, and this equals to this equals to let me simplify this before we proceed. So that gives us r squared, right? So we moved all of these r out, so r squared root 2 minus 1, and the dr d theta. And this will give us root 2 minus 1, 0 to 2 pi, 0 to pi over 2. R squared over 3. And then from 0 to 2. And this will give us 8 over 3, right? So the integral will evaluate to 8 over 3 and the minus 0. So this will give us 8 over 3 d theta. That give us 8 times root 2 minus 1. I'm rearranging a little bit, and then pi over 2 minus 0. So that give us, right? So the 0 obviously drops out, and then we can cancel out the 2. So that just 4 root 2 minus 1 over 3. And that is the correct answer, and that is the answer. Bravo. And that is question number 5. All right, question number 6. By converting this triple integral into spherical coordinates, one obtains this integral, and then the b and the a, b, and c are the upper bounds of the triple integrals in spherical coordinates, and then b times c over a equals. So first of all, don't be scared by this whole thing. At the end of the day, this is just x, and this is just y, and this just z expressed in this spherical coordinates, and then this is your conversion factor. So all we need to do, oh, by the way, let's start with keywords. So keyword is obviously, spherical, right? But we also notice that actually it's this one doesn't really have the terms I'm looking for, but usually, when you see something x squared plus y squared equals to z squared, that usually equals to the rho square, which is the radius of the sphere squared, right? And then if you take the square root, and that's just rho. So obviously this is just triple integrals and spherical coordinates problem. So, okay, so let's go ahead and get started. Right, as usual, we will go ahead and draw the region first. Traces and traces will be helpful, right? If the lower bound of z equals 0, right? In this case, it is, so that's z equals to 0. So let me go ahead and paste this. So we'll draw the region and then start with the traces. If the lower z bound equals to 0, and the most helpful trace has the intermediate integration variable as the vertical axis, and the outermost integration variable as the horizontal axis. So in this case, we have dy as our intermediate variable, and then dx as our outermost variable. So they will be our vertical axis and horizontal axis of the trace respectively. So let's take a look of the trace. All right. So what do we have? So as we know, this will just x2, and this is just x1. This is y2. This is y1, and then this is z2, and this is z1. So x2 and x1, so they are -1 and 1. So that's -1 right here, and then +1 right here. And our y square, we can play the trick again, right? Y2 equals to square root of 1 minus x squared. Y squared equals to 1 minus x squared. Y plus x equals to 1. Oh, they are squared. And you can do the same thing as y1, but it should be pretty obvious that this is a circle that extends both above the x-axis and below the x-axis. So this will be a full, complete circle. Okay. Let me be more precise right here. Move this vertical bounds over. So that concludes so from this diagram we know that we can see that the r bounds, sorry, not the r bounds, the theta bounds, the theta bounds are 0 to 2 pi, right? But also, just for the sake of convenience, actually, this is going to be a very nice handy trick for spherical coordinate integration. Usually, we talk about traces. We talk about x, y, x, z, y, z traces, but there's another trace that the professor doesn't teach you, and that is this is what I call the z. So this I'm gonna zr trace. So let me draw this out for you. To demonstrate what I mean. ZR trace, and this is YX trace. Okay, so what does this mean? So so you might wonder, what does ZR trace mean, and which direction are we looking at it? So actually, this R is nothing different than your X and it's Y. And then so that means we are looking at this diagram sideways. And then by taking advantage of the axisymmetry property of objects in cylindrical and spherical region, we can just looking at it sideways regardless of which orientation we're looking at. So we can look at the axis, we can look at z-axis, zx trace, we can look at zy trace. It's the same thing as looking at zr trace. So with that brief introduction, so I guess with this introduction, I think you can agree that this is just the rho. If I draw a radial line out, and this just be the radial line in the spherical coordinate, and the angle from the positive z-axis to the radial line, and that's just be our phi angle. So now I think you start to realize how helpful and powerful this special ZR trace diagram will be. So with that said, we are going to need to find Z and R, right? So from our XY trace, we can tell that this is 1 and this is 1. So obviously this is 1 and 1, 2, 1, negative 1, negative 1. So we know from the XY trace, we know that the upper bound of R is just 1 because the maximum radius is just 1. So we're going to do that here. We're going to draw that out right here. So 1. And then we're going to extend up. Right, so let me go ahead and then move this away and then make a new one. For demonstration purposes. Okay, so R equals to 1, and then what is our Z? So our Z looks like something of, let's start with Z2. Z2 is square root of 4 minus x squared minus y squared, and then we square both sides. This will give us z squared equals to 4 minus x squared plus y squared, and then x squared plus y squared plus z squared equals to 4. So I think everybody can agree with that. Rho squared equals to 4, so it's a sphere or its radius of 2. But we can also play with the trick that because in the cylindrical coordinate conversion, we know that x squared plus y squared equals to r, right? So x squared plus, so we can convert this sphere expression into r squared plus z squared equals to 4. So this looks like a circle to me. Think about this as x squared plus y squared equals to 4 in our xy trace. So and we can also utilize the z1, the bottom bound of z1, which is square root of 3. Z1 equals to square root of 3 x squared plus y squared, and that's just square root of 3 r, right? X squared plus y squared square root, that's just r. So z equals to r. So that looks like a straight line in my zr trace. So let's start with this blue line, right? Z equals to square root of 3r. So I'm gonna slant it, draw it a little bit more slanted. So z equals to root 3r, and my purple, and then I'm gonna make this circle, rho square equals to 4. So rho equals to 2. I'm gonna draw a circle, which is right. So something like this. So actually, I'm gonna remove this one. So this is radius of 2, radius of 2. But obviously, obviously we are the bounds of the circle is because the fact that we sorry, let me phrase my language a little bit. That so the radius of the sphere is 2, and it's intercepting with this blue line, z equals to root 3 and if we play with some algebra, right? So that z equals to root 3 of r. So if you extend this down, so that's 1, that's root 3. So that means the angle over here will be 60 degrees, and that's pi over 3. And then, but this is not the angle of phi, and the angle of phi is measured from the positive z-axis. So so that means this angle is 90 degrees, which is pi over 2 minus pi over 3, and that's just pi over 6. So and then again, let's use that. Let's use the laser analogy to help us identify the region of integration, right? So I'm shooting up a laser, right? I can shoot up, and that means my theta equals to 0. And then I can reach up to the radius of 2. So, but I can rotate this laser. I can continue to hit our radius of 2, but I must stop at this blue line, and that means my angle, the maximum angle of phi is pi over 6. So with these two diagrams, we can conclude that theta 1 equals to 0, theta 2 equals to 2 pi, right? So we play the laser analogy here, right? We can shoot our laser from theta equals to 0. We can continue to shoot our lasers across pi over 2, across pi, across 3 pi over 2, and all the way reach to 2 pi. So that's bound number 1. And then bound number 2 is the phi angle, right? So and we just found it over here that phi 1 equals to 0, measuring from the positive z-axis, and then phi 2 equals to pi over 6. And then finally, the rho, right? Rho, it's 1 equals to 0, and then rho 2 equals to 2. So again, we don't, by just drawing the traces, we have already found all of our bounds, and we don't need to draw the isometric view, but just for the sake of completion, and then to demonstrate what we're looking at, I'm going to draw it for you this time. So let's move the bounds over. So I'm gonna, copy and paste what we did over here as well. Right, so isometric view. So I'm gonna just make this a little bit bigger. Okay, so we are looking at something that's axially symmetric at this with this slanted line. So it looks like if you revolve this line with respect to the z-axis, it looks something like an ice cream cone. I think you would agree with me about that. So it just looks something like this. It looks like an ice cream cone, and you revolve it around the circle, right? You revolve it around the z-axis, and so that's the bottom side. So what about the top side? The top side is covered by a sphere, right? So let's draw a sphere of radius of 2. So let me move the z-axis a little bit higher. So let's draw a sphere of radius 2. So something like this. And we're going to cut off all the spheres that's beyond the cone, that's beyond ice cream cone. Right, so cut off, 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 cut off. So, and then we also, because we are not going to be able to see what's behind the ice cream cone, because it's covered by the kind of like the ice cream on the cone. So we can also hide this part, right? So this is the region of integration, right? So again, it's good to know, but at the end of the day, it's not exactly helpful for us to find the region of integration, but it nonetheless helps us to paint a picture of what we're looking at. Again, we are going, so actually the second step I already finished for you, so that's just find the bounds of integration. Right, so rho belongs to rho 1 and rho 2. And then R belongs to phi belongs to phi 1, phi 2. Make this a little bit smaller, save some space. And then theta belongs to theta 1 and theta 2. So we can go ahead and assemble the integral, right? So we can start by drawing these three integral signs, and then f of rho phi and theta. And then the conversion factor is rho square sine phi, right? Move this down. D rho d phi d theta. And then 0, 0, 0. Actually, let's start over. So theta 1 is 0. Theta 2 is 2 pi. And then phi 1 is 0. Phi 2 is pi over 2, pi over 6. And then rho 1 is 0, and rho 1 is 2. So, and that's our ABC, right? So that's, the upper bounds are ABC, so A equals to B equals to C. So they want to find BC over A. So BC over A equals to, BC over A, that's just pi over 6 times 2 over 2 pi. Right. So let me color code that as well. And that's just, let's cancel this, cancel that, cancel this, cancel that, and that's just 1 over 6. Yep, and that is the correct answer, which is answer echo. And there you have problem 6. All right, question number 7. Find the volume of the solar region enclosed by the surface rho equals to 12 cosine phi. So by looking at this question statement, the obvious giveaway is this equation, right? They are all expressed in the spherical coordinates. So that's one of the key words that we can find, right? It's a spherical and it contains spherical coordinate variables. And if you remember, other hints might include these rectangular to spherical conversions. So this question is obviously triple integrals in spherical coordinates. So let's start with solving steps, right? The solving step is the same as usual for your for any type of triple integrals and double integrals. I mean, it's particularly triple integral in this case. Right, we're gonna draw the region first, right? So we can start with drawing the traces. And in this case, because it's spherical coordinates, we can take advantage of its axial symmetry by creating this special trace called ZR trace, and then the R is just no different than X and Y, and then we can find the phi from the positive Z axis, and we can find the rho, the radius, by measuring from the origin. So let's go back to the question. The surface is rho equals to 12 cosine phi. How does that even look like in the ZR trace? On the ZR trace, like what does even this cosine mean? But hopefully you will remember from your pre-cal or calculus 1 and 2 that there is there's an equation that looks like this: R equals to cosine theta. And what does this look like? This just looks like a circle displaced to the right on the xy axis. And we can prove that by doing this radial line, right? So if we set theta equals to 0, right? So that's just 1. So our radius is 1. So that's 1. But if we rotate this radial line, we can continue to see that its radius is getting smaller. It's getting smaller and smaller and smaller until we reach pi over 2, boom, 0. And then we continue to increase our radius, and then we eventually will reach back to 1 when we reach theta equals 2 pi, which is essentially 0. But the theta is measured from the positive x-axis, right? So if I have a radial line, right? So the angle is measured from the positive z-axis. So if we translate this idea to the ZR trace, that would give us a sphere or a circle laying up, because think of our x-axis as our z now, because that's where the angle is measured from. So we can do the same thing here, right? Join radial line and then find our phi. And if we let phi equals to 0, right? If we let phi equals to 0, we will get 2 pi. If we let phi equals to 0, our rho will become 12. So that's 12. So, okay. Hopefully this makes a clear image for you. And we can also go ahead and draw the isometric view, right? To help us get a better picture of it. So let's construct a isometric view. Right, so x, y, z, and this is just a circle lying above the xy axis. So this is what we're looking at. All right. So now we have the traces and then the isometric view. Now we can go ahead and find the bounds of integration. So let's start with looking at the traces, right? So and then let's start. You know what? Let's start with the isometric view this time, because look, this is a sphere and it's axisymmetric, and there's no specification or constraint on my theta. So what should my theta be? All right, so theta 1 should just be 0, and then theta 2 should just be 2 pi, because we can revolve around the z-axis 360 degrees, right? No problem. Okay, so let's now look at the phi angle. So, right, let's again use this radial line starting from the positive z-axis. So that's my 0, right? I can continue. So starting from here, my phi is 0, and I keep measuring, and then all the way up to here, right? So what is this? This is pi over 2, right? So I can join this very short line, and this is pi over 2. So now, and I can no longer go down, right? I cannot. This radial line can never go down below the x and the r line, because the sphere essentially doesn't exist below the r line, the r axis, and you cannot. Even though we can stretch to this side, even though we can stretch our radial line to the left-hand side of the z-axis, we shouldn't do that, because remember, our phi, the range of our phi is from 0 to pi, right? So if we go across this line, we are essentially passing the pi, the range of pi, because pi is right here, and then so the pi angle is right here, and then this everything above here, everything on the left hand side is beyond the range of pi. And just for the sake of completion, and to assure you that I'm correct, is because the reason that we shouldn't pass the pi is because once we start revolving around the z-axis with the d integral dd theta, we don't have to pass the pi, because the left hand side will be fulfilled once we start to revolving using the integral dd theta. So the range of phi should be phi1 equals to 0, and then phi2 equals to pi over 2, as we discussed, right? So like almost to the extreme, to the near extreme, that pi over 2 is our upper bound. And what about our rho though? What about our rho, right? So let's start from 0, right? We start from 0, theta equals to 0, and then our I cannot tap. Yeah, but there it goes. My radial line is 12, right? When my theta equals to 0, my rho is 12. But as I keep increasing my rho, increasing my phi, my rho start to decrease, and all the way down to 0. So my upper bound of rho is 12, and my lower bound of rho is 0. Rho 1 is 0. Rho 2 is 12. So now we can go ahead and put them up together, right? And then 3, right? We need to find the volume of the solid region, so we need to assemble, convert. I'm just gonna assemble the integral. Right, so 3 integrals. And then because we're trying to find the volume, the integrand is 1. And then our differential in spherical coordinate is rho square sine phi d rho d phi d theta. And the theta 1 is 0, 2 pi, and then 0, pi over 2, and then 0, 12. And then let's finish the integral really quickly. So right, so rho square integrate, this is rho 3 over 3 sine phi, and then so from 0 to 12, and that's d phi d theta, and this will give us rho 3, 12 to the cubic, that is 1, so 12 squared, that's 144 times 12 over 3, and then minus 0. So this whole thing is rho cubed. And minus, of course, minus 0, right? And then d phi d theta equals to 0 to 2 pi. So sine, integral of sine of is becomes negative cosine. Oh, actually, I take that back. The upper bound of rho is not 12. The rho is increasing, is changing, right? The upper bound of rho is not a constant, right? As you can see, the length of rho of the purple line, is changing as we change in the as we change in the phi. So the actual rho 2 should just be the equation itself, 12 cosine phi, 12 cosine So now we have corrected, and let's assemble the integral. So this will give us, actually, so let me just we get rid of the bottom bound, that's just 0, and then times cosine phi to the cubic, right? So that's our actual integral. Sorry about that, didn't realize it. And then we can use u substitution, right? So u equals to cosine phi, and then du equals to negative sine phi d phi, and then d phi equals to du negative sine theta equals to, right, copy this down, sine phi, and I have no idea what this is, but it's a constant, so I'm just gonna move it to the front. I don't even bother calculating. Sine phi u cube, right? That's cosine cube, and then times d phi, and that's just du negative sine phi, and then the phi cancels out, theta. So that will give us the negative 144 times 12 over 3, 0 to 2 pi. And then u to the fourth, and that is cosine phi to the fourth, and then over 4, and then negative sign. I'm moving the negative sign to the front, and then from 0 to pi over 2 equals to, copy this whole thing down, right, and then d theta, and then so this will evaluate to, let me put the integral first, 2 pi, so cosine pi over 2, that's just 1, right? 1 to the 4th power is just 1, minus minus 0, cosine is, cosine of pi over 2 is 0, and then minus 1, because cosine of 0 is 1, and then divided by 4. So d theta. So I'm going to move the 4 out, and then you can see that negative 144 times 12, and then 3 times 4, right? 3 times 4, that's 12, and that's cancel out, 0 to 2 pi. That's just negative 1 d theta. That's just negative 144 times negative 2 pi, or 2 pi minus 0, and they cancel out, the sign cancels out, give us 288 pi, and that is the correct answer, which is alpha. And then that is the end of question number 7. Question number 8. Calculate the mass of the tetrahedron with corners of these 4 points whose mass density is rho equals to 2z. So the main giveaway of this question is its density, right? It's in a 2z, and its rho is in the xyz coordinates. And also it's a tetrahedron. That means it's very unlikely that we are going to be able to use cylindrical coordinates and spherical coordinates to effectively to solve the problem. So these are the two main giveaways, right? It's a tetrahedron, and also the rho is expressed in terms of x, y, z. So this is obviously and type a triple integral in rectangular coordinate problem. Or you can think of it as a mass integral for mass calculation problem, but essentially that boils down to a triple integral. So the solving steps. So usually we start with drawing the region, right? But does the question give an integral to find the region, or does the question give us the region of the integral explicitly? None of it, right? We have 0 of that. But we do know the vortex, the corners of the tetrahedron, and then that can help us to define the shape of the tetrahedron as well as finding the bounds of the integral. So let's go ahead and start with that. So define the region. So let's go ahead and then draw the tetrahedron out. You know what? Instead of saying that, I'm going to go down and then draw the region. So draw the region, right? Traces, and then if the lower z bound equals 0, which is in this case, the most helpful trace has an intermediate integral variable as the vertical axis and the outermost integral variable as the horizontal axis. You know what? I'm going to switch the order here because I think isometric view is going to be more helpful for us to get started. It's because we have the corners of the tetrahedron, and then that can help us to define the intercepts of the tetrahedron. So let's go and get started. I'm gonna draw a big one for you. So what are the points? So first one, 0, 0, 0, and then 1, 0, 0. So 1, 0, 0, 0, 2, 0, and then 0, 4, 0, 0, 4. Right, this is when the isometric views start to become helpful. So now what we're going to do is we're going to connect these 3 points and then find to create our tetrahedron. So now we're going to find the traces based on the tetrahedron. But this is something to be, most people would just go ahead and get started with the XY trace because they never gave us anything, right? They never gave us anything. Why not just go ahead and start with XY trace as usual? But this is a big mistake here, and because let's pay attention to the integrand that we're integrating, right? So let's, for example, our triple integral is 2z dz dy dx, right? So I think this is what most people would start integrating with. The issue with this integration order is you are complicating the integral by messing with the z variable, because I think you agree with me that these upper bounds are going to be very, very messy. They're not going to be constants, and let's say, I have some sort of plane that looks like, x plus y plus z equals to 1. That gives us z equals to 1 minus x minus y, and 1 minus x minus y is right here. So once I integrate with dz, I would get what? I would get z squared, right? And then I integrate was from 0 to 1 minus x minus y, and then I would get something that looks like 1 minus x minus y squared dy dx. Right, this is and you can see, like, this is another, let's say this is a functions of, y equals to 1 minus x. Like, this integral gets very complicated very quickly. And how are you supposed to integrate this expression analytically? You can't. Chances are you can't. So what we actually supposed to do is whichever variable shows up in our integrand, right? So in this case, z, right? So we should integrate dz last. Keep z as a constant throughout integration until the very last integral. And that will make our life a lot easier. And so you can choose dz dy dx or dz dx dy. The choice is up to you. But for me, take that. I don't know what I'm saying. You can choose dx dy dz, right? Saving the z at the very last, or you can do dy dx dz, right? Again, saving the z at the very last, but switching the order of integration for the innermost and intermediate variable. Personally, I would go with dy, the first option, because as we discussed before, right, the most helpful trace has intermediate integration variable as the vertical axis and the outermost integration variable as the horizontal axis. So translating this into a diagram here, right? So dy dz, yz are my intermediate and outermost variable, and then z and y are just standing up right here. So instead of looking it down, right, looking it down like that, it gets a little bit confusing. Instead of looking like this way, it's a little bit confusing to me. I would rather just like looking at it, directly at it. So the key is, do not integrate dz until the very last integral. So with that said, let's proceed. So we also figured out the most helpful trace is going to be the yz trace. But do we have anything to go by? Like, do we have any equations for us to draw the yz trace yet? No, right? We haven't even figured out what's the equation of the surface that's bounding the tetrahedron, right? This surface bound created by this triangle. So our goal right now is to find that expression of the surface. How are we going to do that? Well, if you remember, all we need to define a plane is a vector and a point. And then that vector has to be the normal vector of the point. So how are we going to find the normal vector? Well, to find the normal vector, we can use the cross product. What are the two vectors that we're going to cross with? Well, if you notice, these three lines are inside the plane. And then if you cross product any of these vector, if you cross any vector that's expressing the line, you can get the normal vector. So let's start finding the vectors. So I'm gonna find vector of this. So I'm gonna label this as A, B, and C. So AC will give me AC will give me so that will be 1 minus so C, so the x coordinate is C is 4, sorry, C is 0, 0, 4, and A is 1, 0, 0, B is 2, 0, 2, 0. So AC is C, this point at the coordinate at C minus the coordinate at A, so that's 0 minus 1, 0 minus 0, 4 minus 0. Right, that's one vector. How about AB? Right, so that's just the coordinate of B minus coordinate of A. So that is just 0 minus 1, 2 minus 0, 0 minus 0. And the AB will give me, I'm going to cut it first and then move this over. Right, AC and AB. So that equals to -1, 0, 4. This will give me -1, 2, 0. All right, so we need to find the EQ of the plane. So that's step 2. So 2.1 is to find two vectors in the line, in the plane. In this case, is R, AC, and AB. Right. And then cross product. Find the normal vector. So that's just normal vector equals to AB cross AC equals to, let's do the determinant. So I, J, K, -1, 0, 4, -1, 2, 0. And that equals to, so for I is we cross this, so we have what's remaining, so 0, 4, 2, 0, I hat minus, right? Always don't forget that minus. So we have crossing the J out, so what's left is -1, 4, -1, 0. And then J hat plus, and then we cross the K out, right? Crossing the K left, cross and down. So what's left is -1, 0, 1, -1, 2, K hat. This should give us the normal vector of the plane. That's just 0 times 0 minus 8 I hat minus 0 plus 4 J hat and then plus -2 minus 0 k hat. So that will give us -8, -4, -2. Right. So let me move this down to that will come back. That will come later. So find a normal vector of the plane. Just for the sake of computation easy, right? Make my computation easy. So what we actually just found is the inward pointing normal vector. So like the vector will point something like this, right? It points into the origin, into the plane. But we can just, it's the same thing as the opposite. When we trying to find the equation of the plane, the opposite of this vector also works. It's just now outward pointing normal vector of the plane. So I'm just gonna say n equals to -n, I'm gonna say n equals -n. You don't have to do this, but I'm just making my computation a little bit easier. 8, 4, 2. Okay. All right. So 2.3. Find the equation of plane. A point and a normal vector. Right? So equation of the plane is as follows, right? So nx x minus a plus ny x minus b plus nz, or you know what, let's make this capitalized, normal vector, right? Y minus b, z equals minus c equals to 0. So, and then we can just find a random point in the plane. So why not just use the coordinate a, right? So that's 1, 0, 0. So that will give us 8 x minus 1. Is that right? Yeah, 1, 0, 0. So x minus 1 plus x minus 1 plus 4y minus 0 plus 2 z equals 0. Z minus 0 equals 0. So simplify that. That will give us 8x plus minus 8, or 8x plus 4y plus 2z minus 8 equals to 0. All right, so now we found the equation of the plane. So we can go ahead and go to step 1 and find the traces. So remember, we want to integrate dx, dy, dz, or dy, dx, dz. I chose dx, dy, dz, so I'm going to construct the dx, dz, the dy, dz trace. So dy, dz trace, so we have the equation of the plane right here, copy and paste. Right, so that, if we set that equals 0, so that will give us, never mind. 8x plus 4y minus 8 equals 0. Sorry, not set it equals 0. You can see, like, I'm also getting a habit, right? So let's set x equals 0. So now we have 4y plus 2z minus 8 equals 0. So simplify that, we get 2y plus z minus 8 minus 4 equals 0. Z equals to 4 minus 2y. So that is our equation of the line. So 4 and 2. So now, so now we can find the the never mind. That's the traces that's going to help us to find the bounds. So let's go to step number 3. Right, step number 3 is just find the bounds. So again, traces contain one-dimensional and two-dimensional informations, which are helpful to find the constant bounds on the outermost integral and the intermediate bounds of the middle integral. So let's go back to the trace, and let's start with our outermost integral. So outermost integral will be dz, right? So we'll integrate with dz last. So z will be our constant. So the highest z we can go is 4, and the lowest z we can go is 0. So our z bounds will be z 2 equals to 4, z1 equals to 0. Okay? And then for the y bounds, of course, we need to write down z equals to 4 minus 2y, or we need to write this in terms of, we need to express y in terms of z, which will give us y equals to 4 minus z 1/2, and this will give us y equals to 2 minus 1/2 z. So y equals to 2 minus 1/2 z. So y2 is 2 minus 1/2 z, right? So if you look from the y side, we're going from left to right. Going to left to right. So the lowest I can go is y equals to 0. The highest I can go is this purple line, which is, y2 equals to 2 minus 1/2. Sorry, 2 minus 1/2 times z. So y1 equals to 0, right? So that's why traces is super helpful for us to find the bounds. So I'm gonna copy. I'm gonna paste it over here. All right, so z2 is 4, and then z1 is 0. y2 is, right, let me color code them. Let me re-color code them. So, right, so the blue, that's the purple, blue, and the blue right here, the blue, and then the brown. Not sure why I use brown though, but you get the idea. So z equals to 0 is right here, right? Z equals 0 is right here, and z equals to 4 is right here. And then y1 equals to 0 is right here, right? So and that's blue, and then this is our region of integration, at least in 2D. Okay, so now we found the intermediate bounds and the outermost bound. We are going to use the isometric view, right? That's why you should construct isometric view whenever possible. And in this case, it's particularly helpful for us to find the innermost bound, which is the most complex bound. But it's not so complex if you have the iso view. So let's go back. All right, so now we know now we know the equation of the plane is just ax plus 4y plus 2z minus a equals to 0, right? So we can paste that here. And remember, you want to find our innermost integral is dx. So we want to express, so our bounds of the integral will be in the functions of y and z. So we should leave x on one side and then yz on the other side. So x equals to ax equals to a minus 4y minus 2z, and then x equals to 1 minus 1/2 y minus 1/4 z. Right? So this, why do we care about x? Because this x will be the upper bound of our integral, which is the equation of the plane itself, right? So if I go up, right, if I from the x-axis I go up, I reach the corner of the line, right? So the corner of the plane, the tetrahedron. But if I go to somewhere over here on the YZ plane, of course I'm going to be limited by the plane of the tetrahedron itself. Again, it's the same idea. If I move to a different location, right, somewhere that's super low, I'm going to continue to be constrained by the plane of the tetrahedron right here. I hope you get the idea. So the upper bound is just going to be x2. x2 is just equation of the plane itself. And x1, right? We always start from the YZ plane. So the lower bound is just going to be 0. So that's your purple. So, all right. So x2 equals to, forgot the equation of the plane. So and then x1 equals to 0. All right, finally, we can go ahead and assemble the integral. And integrate. So this integral looks really bad, but really isn't. To z right here, dx, dy, dz. So 0, z1 is 0, z2 is 4, y1 is 0, y2 is 2 minus 1/2 z, and then x0 is 0, and x2 is 1 minus 1/2 y minus 1/4 z. All right, let's go ahead and chuck this integral away. So again, right, to be honest, I can just even move like the z all the way out, right? But let's not be so quick. Let's just integrate. So 2zy, 2zx, right? So again, right, we're treating as a constant, so it makes things super nice to deal with. 0 dy dz equals, right, so this x is now replaced by this equation. Of course, minus 0, but we're going to ignore that. Dy dz equals to, so now we have, so let me move this over. Let me simplify this expression a little bit. So 2z minus zy minus z squared. So is that correct? Nope, that's not correct. That's 1/2 z squared dy dz. Okay. Okay. And then we integrate again. with respect to y, treating z as a constant. So that will give us 0 to 2, this integral, right? So 2zy minus zy squared over 2 minus 1/2 z squared dy. Sorry, it's from here to here. dz equals to from 0 to 2 pi, so 0 to 2. So wherever I see y, I should substitute. So 2zy, so that's 1 minus 1/2, 2 minus 1/2 z minus z over 2, 2 minus 1/2 z squared, and then minus, actually I should put a y here, equals to minus 1/2 z squared, and then y. Again, of course, every term has a y, so the lower bound of this integral becomes 0, so we can ignore that. dz. All right, let's simplify that a little bit. So that will give us 4z minus z, 4z minus z minus z squared over 4 minus 2 z plus 1/4 z squared, and then minus 1/2 z squared, so that is minus z squared minus plus 1/4 z to the cube, and then dz. So let me check first, see if my integrals are correct. That's y. Then we substitute. Sorry, that's x. Sorry, that's x. That's not y. So that's correct. So we substitute, and then we expanded it. 2z minus z. So 2z minus zy minus 1 to z squared dy dz, and then we integrate with dy, 2zy, and then zy squared, and then z squared y. That's correct. And we substituted it, and then so that's just that, and then we expanded it, 4z minus z, and then minus z over 2 times 4 minus 2 times, that's 1, and then double that, that's 2z minus 2z plus 1/4 z squared, and then 1/2 z squared, so that 2 cancels out, minus sign, plus minus plus 1/2 1/4 z squared z cubed. Okay, that looks correct. So let's continue. Let's continue to simplify it. So let's copy so that's just 3z right here. And then let's move this out. So minus 2z plus z squared minus 1/8z cubed minus z squared plus 1/4 z cubed. Is that correct? Let's check. 242 minus z, negative plus 2 cancel out, z squared minus 1/4 1/8 z cubed, and then dz. So let's go ahead and simplify the terms. So that's z to the first power. So that's 1z. And then z to the second power. So that cancels out. And then d to the third power. So that's 1/4, 1/8 z to the cube dz equals to z squared over 2 plus 1/8 z to the fourth 0 to 2. That's just 4/2 plus 16/8. That's the answer is not correct. I don't think so. 16/8. That's just that's 2 plus 2 equals 6. Equals 4. And that's not one of the correct answers anyway. So something is wrong here. Something is wrong. We'll fix it. Wait, hold on. Is z? Yeah, that's what I'm talking about, right? Z is to the fourth, not to 2. Never mind. I'm very sorry. 4, 4, 4, 4, 4, 4, and 4. Sorry for all of those mistakes. And 0 to 4. So that's 16 plus 6. So 4 to the 12. 4 to the 2 is 16. Sorry, 4 squared is 16, and 16 times 16 is right here, and that will give us 8 plus. Oh, I also forgot a 4 right here. So that's 32. So that's 8 plus, this cancels out. That leaves us a 2, and 8 plus 8. Oh, why is this not it's not a correct answer? Oh, I see. This is a z squared, not a z. So what should really happen is 4z z squared. So what happened to what a mistake is, I ignore the z squared when I multiply 2z over 1/2 z. So this will be a z squared. So 4z d squared, and then everything else is remains normal. So all right, okay. So now let's see if we can arrive at an answer right here. So 4z is minus 2z is 2z, right? So right here. So first power, and the second power is minus z plus z, and then minus z squared. So what should really happen in this integral is 4z minus 2z equals to 2z minus z squared plus z squared minus z squared minus z squared. And then plus 1/2, minus 1/8 plus 1/4 is equals to 1/4 z to the cubic. So, all right. So that will give us z squared, and then plus minus z cubed over 3, and 1/8 z to the 4th. This still doesn't look correct though, because I should have a constant number. But anyway. So that's 16 minus 64 over 3 plus 16 times 16 over 32, which equals to 16 minus 64 over 3 plus cancel, this will leave us as a 2 plus 8 equals to 24 minus 64 over 3 equals to 72 minus 64 over 3 equals to 8 over 3, which is the correct answer for question number 8. So as you can see, this is a very, very tedious, very, very difficult, and very, very long problem to solve. So, but at the end of the day, but which I think this is probably one of the hardest, if not the hardest, triple integral problem they have ever put up. But at the end of the day, it's nothing that we cannot solve so long as we know how, right? So the process of triple integrals is very similar, but we just need to be aware of to find the equation of the plane that's covering the tetrahedron, which is this plane right here, and we also be careful with our order of integration based on the integrand we're provided. Right? If we choose the right order of integration, it will make the integration process a lot easier and actually make it possible. Right? As we demonstrated before, that if we set up the wrong integration order, this integral is impossible to solve. So that is for question number 8. Question number 8. A potential for the vector field F is, so based on the question prompt, it should be pretty obvious that we are trying to find a potential function of a vector field. So the problem type is a conservative vector field or potential function problem. But for a vector field to have a potential function, the vector field itself must be conservative. So before we find any potential functions, we must check whether this vector field is conservative or not. So let's go ahead and do that. So first step 1, check if f is conservative. So let f equals to psi x and psi y, and then equals to sine y, and then x cosine y. Okay. So for a vector field to be conservative, the psi x y must equal to psi of x. Psi y x. If f is conservative. So let's go ahead and check that. So we know psi x is sine y, so psi xy equals to cosine y. Then psi yx equals to cosine y as well, by taking the partial derivative of this with respect to x. So therefore, f is conservative. Now we can go ahead and find the potential function of the vector field, conservative vector field. Second one. So second step. So the first thing to find the potential function is integrate psi x with respect to x to get psi x and psi y, psi x plus psi x of y plus c of y. So let me write that down. Psi x plus c of y. Okay. So the reason why there's a cy exists is because when we differentiate our psi to get our psi x, anything that only contains the y term gets lost because we treat it as a constant when we differentiate. So we must include the c of y to complete the picture of psi. All right, so that will give us integrate sine of y dx equals to x sine y plus cy. Okay? So, and then once we obtain this equals to psi of xy plus cy, we need to differentiate this thing that this term that we just obtained with respect to y. Respect to y to get psi partial x, partial psi, partial y, partial c, partial y. So partial y, right? So let's differentiate. So differentiate with respect to y, that will give us x cosine y plus cy of y. And this should equal to psi y. And psi y also equals to cosine x cosine of x. So by comparison between the left-hand side and the right-hand side, we can conclude that partial c partial y equals to 0 because the rest of them equal to each other. And so that means integrate 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 cy of y with respect to y to get cy. And obviously integrate cy of y dy 0, because cy of itself is 0. So now our final step is to assemble psi y, psi xy, and psi y. So our psi y is already x cosine y, x sine y right here. But our cy, we just determined that it's equal to 0 from step 4. So our sine, so our psi xy equals to x sine y plus 0. So if we look to our solutions list of solutions here, there isn't an exact solution that matches our answer, exact choice that matches the answer. The closest one will be answer echo. So, and with a +1 remain on the right. But does it matter? It doesn't matter, right? Because when we integrate something, we can always plus an arbitrary constant. We just didn't include that in our original calculation. So, I could have added a constant over here, but does it matter for my calculation to add a constant? No, right? So I'd rather save that constant to the very end, so that I can vary this value of c to match my answer, instead of getting myself confused in the process of differentiation and integration. So I'll just say let c equals to 1, then psi of xy equals to x plus sine y plus 1. And that is the correct answer for part 9, for question number 9. Oops. All right. Question number 10. Let C be the curve R of t, and the t belongs to 0 and the pi over 2. And the function, so f equals to x times y. Then find the value of the line integral. So this is So this is obviously a line integral problem because of its unique property of ds, right? So ds is for line integral, right? Curve, like integral of curve with another line integral differential, so now we identified it's a line integral problem. We also need to determine whether it's a line integral in scalar field or a line integral in vector field problem. So the main way of differentiating a line integral in vector field and line integral in scalar field is by looking at its integrand. So if an integrand is a scalar, then it's a line integral in scalar field. If it's a vector, then it's in scalar field. In vector field. So in this case, we have fx. So this should be fx xyz. Okay, this is a typo right here. So f is obviously a scalar. So this is an line integral in scalar field. So let's go ahead and solve it, shall we? So the first thing we need to do in this case, in this question, we can safely ignore is find expression of line R of t. Okay, and the range of t. Sometimes it's explicitly given. In this case, it is. We know R, we know t range, but sometimes it's not explicitly given. So we need to be able to find that if it's not explicitly given. Then we need to find r prime of t. And then r prime of t, then r prime of t magnitude. Okay, so how are we gonna? So let me go ahead and copy the curve down. So r of t equals to cosine of t, sine of t, t. Right, so then r prime of t equals to negative sine t cosine t 1. And then the magnitude of that is r prime of t magnitude equals to square root of negative sine t squared plus cosine t squared plus 1. So that's just 1 plus 1 equals to the square root of 2. Then we will parameterize the function with respect to t. So how are we going to do this? So let's go ahead and copy the function down. So f equals xy. So we are going to replace x with the x component of the line expression, not r prime though. Just r, the expression of the line, not the time derivative of r. So here's how it goes. Wherever I see x, right? So this is x coordinate, this is y coordinate, this is z coordinate. So wherever I see x, I replace with whatever I have in r. So that is that's cosine t, and then y is just sine t, right? Cosine t sine t, and then so basically I'm gonna make sure everybody understands this. So basically replace any x in f. X in f with x of t from the line equation. And then repeat this for any y and the z. Okay. So now this should be crystal clear. Then we are going to assemble the line integral. So our time limit is a to b, right? So this is our standard formula: a, b, f, x of t, y of t, z of t, and then r prime of t magnitude dt. So our range of t equals to 0 to pi over 2. So 0 to pi over 2 right here. And so 0 to pi over 2. And then f now parameterized will give us cosine t, sine t, and then r prime of t. Let me make that clearer. So that times square root of 2 times dt. And now we just go ahead and solve for this integral. You can use trig identity if you want, but I don't think many people will memorize that trig identity, but it's no problem if you don't. We can use the u substitution as well. So let u equals to sine of t, right? Then du is cosine of t dt. Then dt equals to du cosine t. Then this integral will become cosine of t u, right? We replace with u times square root of 2 du cosine t. And then cosine t cancel out. That leaves us with square root of 2 integral u du. That will give us root 2 u square, and that is sine square t over 2. And then the bound is 0 to pi over 2. And then we can further simplify that with 1 over root 2. And then the integral sine of t will evaluate to when t equals to pi over 2, sine t equals to 1. So that's 1 square minus 0 square. That's just 1 over root 2. And that's the answer for question number 10. Oops. All right, question number 11. The final questions of for 2019 exam 2. Let C be half circle x squared plus y squared equals to 4 with s greater than 0. Then evaluate this integral. So, as usual, this is a scalar integrand. X is a scalar, not a vector field, right? So first thing we can tell that this is an scalar integrand. And we also notice that this is a ds, and then the differential is ds, and then the integral itself is integral of c, and that's a curve. So this is a second hint that's telling us this is a line integral in scalar field. So now we know that this is a line integral in scalar field problem. But this time, as compared to question number 10 in this exam copy, is that we now need to find the expression of r of t, because the expressions of r of t and the range of t is nowhere to be found in this question. But it's no problem. We can parameterize ourselves. So that's the first step, right? So first step, find. I'm gonna go ahead and copy and paste it from question number 10 to save us some time. So find expressions of r of t and the range of am of t. So all right. So how are we gonna do that? So we see this C be the half circle of x squared plus y squared equals to 4 with x greater than 0. So let's go ahead and draw that. X squared plus y squared equals to 4, and x has to be greater than 0, so x, y. So it's like a half circle with x greater than 0. So that's 2, and that's negative 2, and that's 2. So this is a standard parameterization technique for unit circle is r of t equals to cosine of t and then sine of t, right? So, but for our circle, its radius of 2, so it's twice as large. So our vector needs to be twice as large as well. So for our problem, the the line equation should be 2 cosine t and then 2 sine t, and the range of the range of t is so this is t equals to 0. So if we go down, we should see t equals to pi over 2, right? Negative pi over 2. And then same idea, if we go up, we should have positive pi over 2. So that's how you obtain the expressions of line of t and the range of t. So now we can go for the second step, which is finding the r of t and then the r prime of t. So r prime of t equals to 2 times negative sine t, and then, no, I'm just going to say negative 2 sine of t, and then 2 cosine t. And then r prime of t, the magnitude would be just negative 2 sine t. You know what? I think we can safely ignore this and then just conclude that the r prime of t, the magnitude is just 2, because r sine squared plus cosine squared equals to 1, and r squared becomes 4, and then take the square root, r prime of t becomes 2. The magnitude becomes 2. So, all right. So then the third step is parameterize the function, parameterize the curve with respect to t, right? So same as the instructions, the solving steps that we discussed with question number 10. We are going to parameterize f of x by t with respect to t, with t, and the way we're going to proceed is replace any x in the function with x of t from the line equation r of t, and repeat this for any y and z as well. So our integrand is f equals to x, right? And this equals to, and because and the x coordinate of the line equation is 2 cosine t, so we're going to replace x with 2 cosine t. And then step number 4, assemble the line angle and a standard equation. Right? So our lower bound we just found is negative pi over 2 and the positive pi over 2 is our upper bound. So negative pi over 2, and then f of t we parameterize would become 2 cosine t, and then 2 cosine t, and the magnitude would just be 2 times 2 dt, and this should be a pretty easy integral to solve. And that's just 4 negative pi over 2 cosine t dt. That's sine 4 sine pi over 4 sine of t pi over 2 negative pi over 2, and this will give us 4. So sine of t at pi over 2 will just be 1, and then minus sine of negative pi over 2 is negative 1. So 1 minus negative 1 will give us 2, and that the entire integral will give us 8. And that is the correct solution for question number 11. And that includes MA 261 Fall 2019 Exam 2 Walkthrough. And thank you very much for watching, and I'll see you next time.